The last little bit of Chapter 4, putting it all together. Chapter 4, as you may recall, is all about precipitation reactions, the solubility rules, oxidation reduction reactions, redox reactions, oxidation numbers, who's gaining electrons, who's losing electrons. And as we did in the last one, acid-base reactions, proton donors, proton acceptors, what's the salt that you make, that kind of thing. So, in this putting it all together category, there are two main types of problems we will see. One is gravimetric analysis, and another is titrations. Gravimetric analysis is usually the result of a precipitation reaction, while titrations are often something that you do with things, species, that can undergo redox reactions or acid-base reactions. So gravimetric analysis is this procedure described here. You have some sort of unknown substance, and you can dissolve that substance in water. So this is our unknown substance is dissolved in water. You don't see any ions, you don't see any cloudiness in solution. Your ions are all completely dissolved in solution. Then you add some sort of substance to that to form a precipitate. So this is some sort of substance being added, and you see how it gets cloudy around that stir rod. That's a precipitate starting to form in that solution. So what's happening is whatever you're adding here is hooking up with something that was already dissolved here in order to precipitate. Then you filter out and dry your precipitate. So this is a vacuum filtration setup, and you get the solid up top and all the liquid filters through to the bottom. You analyze the solid that you collected, as in you can weigh it, and based on the weight of precipitate that you get, you do some stoichiometry, some mole ratio stuff, to convert backwards and figure out how much of your unknown was in this solution in the very beginning. So we're starting with our ending result and working backwards to figure out some initial value about our unknown. The exact same thing is true with a titration. You start with an end result and work backwards to figure out something about your beginning solution. Chloride ion concentration is analyzed by titration with silver nitrate using sodium chromate as the indicator. If this much silver nitrate were used, how many grams of chloride ion are present? So we just walked through a gravimetric analysis problem, and then the first problem we go to do says it's a titration. Why did I do that to us? Well, we're going to talk about a gravimetric analysis problem also, but let's talk about titration. So we're going to know the ending result of the titration is it took this much stuff to get your titration to reach what's called its end point. The end point of a titration is the point when things shift, things switch gears, they switch colors, or some sort of visible change happens. It's almost always changing color. Some sort of visible change happens to indicate that your reaction is complete. So some sort of thing visibly indicates that your reaction is complete. So when this says sodium chromate is the indicator, sodium chromate has no bearing on this reaction whatsoever. It just says, sends a signal, a visible color change signal saying your reaction is finished. So that little bit is totally extraneous information as far as what we're trying to figure out, the grams of chloride ion present. Indicator is just something that's absolutely essential in the titration, but irrelevant as far as the math we're going to do. So if we start with 44.2 milliliters, that's 0.0442 liters of silver nitrate solution, 0.71 moles of silver nitrate in 1 liter of silver nitrate solution. How many grams of chloride? Well, we need to relate moles of chloride and moles of silver nitrate. I just went off to the races with all the numbers and we had no discussion of how these things react together. I think it's kind of reasonable to start with a reaction, don't you? chloride ion concentration is analyzed by titration of silver nitrate. This is where I was saying this sodium chromate does not matter. Do not put sodium chromate in your equation. We've got silver nitrate reacting with chloride to make silver chloride, and physical state is important this time, and I guess I should say aqueous for those two, because silver nitrate is a soluble salt. And I'm going to get some nitrate ions free-floating out of it. So we're trying to detect unknown chloride by precipitating silver chloride. So, is it balanced? Yeah, it's balanced. So 1 mole of silver nitrate for every 1 mole of chloride, and I actually just realized I wrote this upside down. That should be chloride up top and silver nitrate on the bottom. What am I thinking? Oh boy. I'm half asleep. 1 mole of chloride for every 1 mole of silver nitrate. So there are how many moles of chloride in our unknown solution? Do that math. I wait. I got 0.0314 moles of chloride. Well, this says how many grams of chloride ion. I could have continued my top red string up there, but I was running out of space. I don't want to know moles of chloride in the end. I want to know grams of chloride in the end. And 1 mole of chloride weighs 35.45 grams. So how many grams of chloride ions must have been in a solution? 1.11 grams of chloride ions. Did I even use this sample of river water? No, not at all. So sometimes you're given extraneous information, stuff that doesn't really matter in the long run. But this kind of thing is a titration problem, also a precipitation gravimetric analysis kind of problem, because we're making this precipitate. But we could also give you the same kind of thing where maybe hydroxide ion concentration is analyzed by titration with nitric acid. It's an acid-base thing, not a precipitation thing. So you have to get to the point when you read a sentence like this, you can classify that reaction type as an acid-base reaction, a precipitation reaction, or a redox reaction. In this one, what volume of this HCl is needed to neutralize this NaOH? Is that an acid-base, a precipitation, or a redox? Hopefully you're shouting. Acid-base. So I've got HCl reacting with NaOH to make NaCl, salt plus water. It's a neutralization reaction. It's very helpful that they said that word here, but you need to recognize it's an acid-base reaction even when we are not given that word. This is a balanced reaction already, no further coefficients necessary. So I'm going to start with the end, meaning 10 milliliters. I should have just gone ahead and converted it to liters already, but I'll go ahead and write out the conversion. 1,000 milliliters in 1 liter. 1 liter, though, is 0.3 moles of NaOH. And 1 mole of NaOH reacts with 1 mole of HCl. And 1 liter HCl solution has a concentration of 0.5 moles per 1 liter. So that will tell me the volume in liters needed to neutralize that much HCl. Sorry, that much NaOH. I got 0.006 liters of HCl solution. So that's 6 milliliters of HCl solution. Students often, after you learn dilutions, students often see a problem like this and think, oh, that's just a dilution problem. No, you shouldn't treat problems like this as dilutions because there's an actual reaction happening. Hydrochloric acid plus sodium hydroxide makes sodium chloride and water. There's a reaction. In a dilution problem can never be the way you approach a problem that has a reaction happening. These two things are added together to make new stuff. It is not a simple dilution problem. The spectator ions could be treated as a dilution problem, but hydroxide and H plus that are coming together, that is not a dilution problem. It's a legitimate reaction. Okay, maybe that's enough of my soapbox for that one. What about 10 milliliters of 0.2 molar barium chloride, barium hydroxide? My reaction here is going to be HCl plus barium hydroxide yields water and barium chloride. 2 chlorides for every 1 barium, which means you need 2 HCl's to create 2 waters to make that thing balanced. So instead of starting here with milliliters, I'm going to go ahead and say 0.01 liters of 0.2 moles barium hydroxide per 1 liter. Convert that to 2 moles of HCl are needed for every 1 mole of barium hydroxide. And then, if it's the same solution, 1 liter HCl for every 0.5 moles HCl. It's getting a little crowded down there, but do that little mathy math and you get 8 milliliters HCl. 8 milliliters of HCl are needed to neutralize that barium hydroxide. If you had done this as a simple dilution, you would have come up with the wrong answer because there's a 2-to-1 mole ratio here. Be careful. Okay. Next. This problem, if you're looking for it in your paper, I think it's actually a couple of pages ago on your PowerPoint notes. I apologize, it got misplaced. If 30 milliliters of this stuff is added to 15 milliliters of that stuff, what's the mass in grams of the precipitate? Again, this is a courteous problem that it tells you it's a precipitation reaction, but you need to be agile enough to know calcium chloride is an aqueous soluble salt, and when you add that in with silver nitrate, that's an aqueous soluble salt. But when they do a little do-si-do switching partners, that makes an insoluble exception, silver chloride, and calcium nitrate as a soluble salt. Totally illegible over there. Sorry, got real squishy. This is not a balanced reaction so far. I need 2 of these and 2 of those to make it a balanced reaction. Yeah. 30 milliliters of this stuff is added to 15 milliliters of that stuff. What's the mass in grams of the precipitate? This is a limiting reactant problem. Yeah. This is a limiting reactant problem. You're told concentration and volume of one species and concentration and volume of another species. You need to know who's limiting in order to figure out how much of the final solid you get. So I'm going to pause real quick and rewrite this equation in a more legible form, and then we'll get going with the math. Okie dokie. So 0.03 liters times 0.15 moles calcium chloride per 1 liter tells me how many moles of calcium chloride are in my solution. And you may not prefer limiting reactant this way, but I really like limiting reactant tables because they help me organize my thoughts. So I'm going to put my start number of moles of calcium chloride is 0.0045 moles. That's what I got from that answer. I'm going to do this same thing, lather, rinse, and repeat, just different numbers. 0.15 liters times 0.01 moles silver nitrate per 1 liter gives me 0.0015 moles of silver nitrate. I'm not sure what I just said, but I may have just said that wrong. 0.00015. I think I said too few zeros that first time around. That's my starting moles of reactants. And my starting moles of products is I don't have any. That's 0, 0. Change in terms of x. That's minus x minus 2x plus 2x plus x. Do you remember how to solve for x in a limiting reactant table? Set your things equal to 0. Yikes, I can't talk and write at the same time. Set your things equal to 0 and solve for x. 0.00015 minus 2x. Hopefully you can already tell who's going to be the limiting here. X equals 0.00075. This starts to be the point where we need some scientific notation probably. 7.5 times 10 to the negative 5. Yeah. This number is way smaller than that number, so this is my true X value. Plug that in and get my final in terms of moles. Okay, let's clear up some space and do this. So we've got, oh, I need a calculator for that. 0.045 minus 7.5 times 10 to the negative 5. 4.425. Let's keep it scientific notation. 425 times 10 to the negative 3. This guy is 0. This guy is 0.00015. And this one is 7.5 times 10 to the negative 5 moles. And which one is my precipitate? Because my question is, what is the mass in grams of the precipitate? This 0.015 is my precipitate. So I need to know how many grams of that thing. So 0.00015 moles AgCl times 1 mole of AgCl weighs, I got papers here somewhere, 143.35 grams. And that should give me my final mass of precipitate. See if you got what I got. .015 .022 grams of AgCl. Is that a lot of precipitate? No, not at all. But we got some precipitate. Whew. So these titration and gravimetric analysis problems can be a lot. They can be long. They can be overwhelming. They all assume that, number one, you can classify reactions by type, precipitation, redox, and acid-base. They assume you understand molar mass and mass ratios and how to balance equations. They assume you understand molarity and concentration relationships. And they assume you understand limiting reactant relationships, like this one we just did. It's a snowball effect. If there are any of those old topics that you're still shaky on, we got to get solid on them before this next round of quests with our gravimetric analysis and titrations being a part. Whew, that's a lot. Ta-ta.